Hello, I'll be going through most of the problems on practice exam 2 in this video. I think I have about an hour. For whatever reason, my phone doesn't want to record past an hour so far, at least the last couple times. So I'm gonna get right into it. I'll just do the problems I do, and then of course you can see the full key. You can find that actually, I think, already on Canvas, but you can see it next to this video also. So derivatives, just straight up taking the derivative in this first problem. So f prime of x, this is a constant, e squared. There's no variable involving x here, so this is a zero derivative. F of t, I'm going to go term by term. There's no real fancy rule that we need to apply. So I'll have f prime of t. I'll use the power rule, bring down the -5. T, reduce the power by 1, so that actually becomes a -6. Bring down the 3, I have -2 t squared plus 2 derivative of pi with respect to t is 0. This would be fine. If you wanted, you could rewrite this with a positive power. So you could say -5 over t to the 6th minus 2t squared plus 2. For the exam, read carefully. Just read carefully and make sure you're working within whatever it was stated. So this one, you could use the product rule or you could expand first. So I'll just think of g itself as x cubed plus x squared minus 2x. I'll get a -2 and then I'll add 1, so -1. So this is g prime of x. I haven't evaluated or calculated yet, but power rule, 3x squared plus 2x minus 2. Here, again, another power rule. We have some negative exponents, but that's okay. We just multiply down, reduce by 1. So p prime of z, -15 halves z, -3 halves minus 2 halves, -5 halves. Multiply down, -z to the -3 halves. Derivative of 5 is 0. So, or if the instruction was to leave this with only positive exponents, then you would want to write -15 over 2z to the 5 halves, the positive 5 halves now, minus 1 over z to the positive 3 halves. That's a -15 there. Okay. So I'll do apparently this whole problem. Rethinking of h. So before taking the derivative, I can simplify a bit. So I can say x cubed. In other words, x to the 4th divided by x is x cubed. X to the 5 halves divided by x. Basically, this is like x to the 2 halves. So subtract 5 halves minus 2 halves. So I get plus x to the 3 halves. And then I can write this as plus x to the -1. So h prime of x will be 3x squared plus 3 halves x to the 1/2. I'm reducing 3 halves by 2 halves minus x to the -2. Again, if the instruction were to use positive exponents, you would have 3x squared plus 3 halves x to the 1/2 minus 1 over x squared, like this. If you guys catch any mistakes on this video, please comment and discuss any potential mistakes below. I'm kind of going through this quick. Obviously hope no mistakes happen, but they do sometimes. So number 2, the equation of motion of a particle is given as this, where s is in meters and t is in seconds. Part 1 says find the velocity and acceleration as functions of t. So the velocity will be equal to s prime of t. So s prime of t will be 6t squared minus 8t. The acceleration will be equal to s double prime of t, in other words, the derivative of the derivative. So we'll have 12t minus 8 for that. So there's the acceleration and the velocity that was wanted. Find the acceleration after 2 seconds. So s double prime of 2. All right, I'm coming here and plugging in 2. So 12 times 2 minus 8. We have 24 minus 8. So 16, and technically we would have meters per second squared. Part 3, find the acceleration when the velocity is 0. So here's our velocity function. Setting this to 0 will give us the times that we're concerned about. So maybe factor. So 0 equals 2t, 3t minus 4. So we're concerned with 2t equals 0 or 3t minus 4 equals 0. So in other words, when t equals 0, apparently the velocity is 0. And or when t equals 4/3, the velocity is 0. So find the acceleration. So sorry, not f, but s double prime, the acceleration evaluated at 0 will be, come back here, 12 times 0 minus 8 equals -8, and this would be meters per second squared. And we also need to find s double prime of 4/3. In a second, I'm going to pull up the key just to make sure that I'm not messing any of these up. Okay. So this is 12 times 4/3 minus 8. 12 times 4/3 is 16. 16 minus 8 is 8. So we have 8 meters per second squared at that moment. All right. So that's number 1 and 2. All right, number 3 is just a simple differentiate problem. So I'll just go ahead and do this. So f prime of y. So we have some chain rule. So this will be exactly itself, since it's exponential base e, but then multiplied by the derivative of 3y. So I have technically d dy of 3y still to evaluate. Here I have just a power function. So I'll have, to multiply down, I'll get 9e times y raised to the 3e minus 1. All right, don't let this fool you into thinking it's an exponential function. So derivative of 3y is 3. So finally, f prime of y is 3e to the 3y. I'm just bringing this 3 out front. Derivative of 3y is 3. And then I have plus 9e y raised to the 3e minus 1. Number 4, find the equation of the tangent line. So for the tangent line, we're going to need a slope. The derivative is our axis into slope. So what I'll do is take the derivative of this given, evaluate it at x equals 1. That'll be the slope at that x equals 1 location. Then we'll use maybe the point slope form to write the equation once we get the slope. So we need y prime. So that equals 1 plus e to the 2x times 2. I'm just doing the derivative part a little more quickly. So e to the 2x, then multiplied by chain rule the derivative of 2x, which is 2. So then evaluate y prime at x equals 1. So I have 1 plus 2 times e raised to the 2 times 1. In other words, our slope, just to keep it in exact form, would be 1 plus 2 times e squared. Okay, so that's m, in other words. All right, so now putting that together, we can write y minus 1 plus e squared, right? That's my y coordinate, equals my slope, which is 1 plus 2e squared times x minus 1. This would be a fine way of leaving it. That's just the point slope version. Differentiate. This is a product rule example. So I'll take the derivative of the first, 3x squared, times the second unchanged, plus the derivative of the second, so I'll leave the first one, and then I'll multiply by the derivative of the second one, which would be e to the negative x, and then multiplied by negative 1, which would be the derivative of negative x. So just to simplify a bit, I can write 3x squared e to the negative x minus x cubed e to the negative x. And you can leave it like that, or you can factor it. So if you factor it, you can pull out an x squared and an e to the negative x. So x squared e to the negative x, leaving behind 3 minus x. This would be one option. Or you can rewrite it with positive exponents. So you could say x squared, 3 minus x over e to the x. Okay. Differentiate. I'll do both of these. So here we have a product of functions of x. Here's one function of x, here's another. So what I'll do is, similar to the previous one, is I'll take the derivative of the first. So this is now f prime of x. So 8x cubed times the second unchanged, and then add the first unchanged times the derivative of the second, which is pi raised to the x times ln of pi. And then, yeah, I would need to multiply by the derivative of x, but that's just 1. So this would be fine with me. You can leave it right here, actually. And I'll do that just to save us some time. Part 2, again, just differentiate. So quotient rule. So g prime of t will be low d high. So here's the low d high, meaning in this case I'll have 10 t to the fourth, low d high minus high d low, in other words, e to the 2t times 2 because of the chain rule. I'll get that 2 from the derivative of 2t over the low one squared. I'll factor and simplify this one. So I have a 10, I have a t to the fourth, a t to the fifth, I have a 4, and an e to the 2t in both. So I can definitely take out a 2 t to the fourth, e to the 2t, leaving behind a 5, minus 2t, I believe, is all that's up there now. And then over e to the 4t, I'll just simplify that. Now I have an e to the 2t. Really, it might have made more sense just to leave it. So let me go back. So I'll write it as e to the 2t squared still. Now what we can do is actually cancel a copy. Right, so e to the 2t, I have those squared down below. So in other words, I have 2t to the fourth times 5 minus 2t over e to the 2t. Okay. Number 7, this is going to be the first one where I don't do everything. I will do part 1. I'm not going to do part 2. Please reference the key for part 2. So f prime of x, I have a product of functions of x here. So to find f single prime, I will need to use the product rule. Keep in mind that this is the same as 2x to the 1/5 power, this piece here. Okay, so product rule, derivative of first, so 1/5, 2x to the negative 4/5, right? I'm reducing 1/5 by 1. Then multiplying by the derivative of 2x by the chain rule, so multiply by 2. So that's the derivative just of the first one. Then I multiply by the second one unchanged. Then I add to that the first one unchanged. I'll just write it as 2x to the 1/5. And then times the derivative of the second. So e to the 4x times 4. I'll do my best to kind of clean this up and factor, because unfortunately we need to calculate f double prime also, so the second derivative of this. So you want the first derivative to be as nice as possible, so that way when you take the second derivative, it's a little bit more user-friendly. So I'll go ahead and rewrite this just a bit as 2/5. Yeah, maybe I can factor out, well, let me simplify actually. So e to the 4x, 2x to the negative 4/5, plus, and then we have, I guess I'll write it as 4e to the 4x, and then 2x to the 1/5. All right, so factoring, I'll leave the 2/5 and the 4, I'm not going to worry about that. But I can factor out a 2x to the negative 4/5 and an e to the 4x. So e to the 4x, 2x to the negative 4/5, leaving behind a 2/5, plus 4 times 2x, I believe, because 2x times just 2x, I'll have, so just to do some scratch work up here, I'll have 2x to the negative 4/5 times 2x just to the 5/5, if you will, just one copy of 2x. This will equal 2x to the 1/5, which is what I need to account for, right? Because that's what I have here, a 1/5. So in other words, it's 4 and then just times one copy of 2x that I need. Sorry if you couldn't see that a second ago. So what I was saying is I was trying to figure out what gets left behind, basically. All right, so looking here, just to simplify this a little bit further, we have e to the 4x, nothing we can do about that, and then times 2/5 plus 8x. All right, I'm looking here and simplifying. This is now all over 2x raised to the positive 4/5. I can bring this down just as long as I change the sign of the power. So this might be as good as we get as far as the first derivative goes. Let me see what I ended up with. The second derivative is really awful. So I'm not feeling like doing that. This will be my first derivative. For f double prime, see the key, please. Okay, so let's go on to number 8, perhaps. Number 8. Differentiate, so kind of a simple quotient rule. So that's a breath of fresh air. So g prime of x low, d high, minus high, d low, over the low one squared. So that's this kind of format, and now we're going to simplify and clean this up. So g prime of x, maybe I'll FOIL this out. So 6x cubed plus 6x squared minus 2x minus 2 minus 2x cubed plus 2x. Okay, over x plus 1 all squared. Simplify. So it looks like I can write g prime of x. I have some like terms, the cubic terms. So 4x cubed, just one squared term. Cancel the linear terms. And just negative 2 is left. X plus 1 all squared. I believe that's it. You could also factor the numerator, but this would be fine. Go ahead and check out the key for part 2. All right, so number 9. So find equations of tangent lines to the curve that are parallel to this given line. Okay, so we need y prime. We're going to need the quotient rule for that. Then we're going to set that derivative equal to the slope of this line, forcing the slope to therefore be parallel to this given line, and then that'll spit out perhaps 2 locations x for which that parallel or that tangent line is parallel to this given line. So we'll figure out the x's from that process, then we plug in those x's to get our y's from this original equation. So that's our outline. So y prime, low d high, minus high d low over the low one squared. Okay, so this is the derivative. I'll go ahead and simplify this a bit. So we have 6x plus 2 minus 6x plus 3, right? Just doing some quick distributing there, over 3x plus 1 all squared. 6x minus 6x, 2 plus 3, looks like I have a 5 over 3x plus 1 all squared. What I need to do is figure out the slope of this line. So if I put that in slope-intercept form, I'll actually get y equals x minus 3. So in other words, the slope is 1. Right? So in other words, I need this to be 1, which means I need this to be 5, and so on. Right? I need this to be the square root of 5, right? Because I'm squaring it. So in other words, 1 now needs to equal 5 over 3x plus 1 all squared. So 3x plus 1 all squared needs to equal 5. Take the square root, plus and minus. So 3x plus 1 equals plus and minus root 5. Solve for x. Divide by 3, finally. So we're getting these two x's. x1, I'll go ahead and call it negative 1 plus root 5 over 3. And then x2, I'll call it negative 1 minus root 5 over 3. These are the two x's for which tangent lines to this original curve are parallel to this given line. Okay, so what we now need to do is plug each of these back in to get our y's. Okay, so I'll do that with the aid of the key here. I'll just go ahead and check one of them. So what I'm doing is I'm plugging this value into this original equation. Okay. So 2 times negative 1 plus root 5 over 3 minus 1, 3 times negative 1 plus root 5 over 3. I think I have an extra fraction in there. I'll just put a 1 in that case. And then plus 1. That doesn't look familiar. So let me try that again. All right, so 2 times fun calculator stuff here. All right, so I'm going to plug this in to the original to get my y for that. 2 times answer minus 1 times answer plus 1. So I'm getting this, 2 minus root 5 over 3. So that'll be y1. So y1 equals 2 minus root 5 over 3. Now, the other one, y2, if you do the same thing, you'll get y2 as 2 plus root 5 over 3. And your two equations would then be y minus y1, which is 2 minus root 5 over 3, equals a slope of 1. So I'll just leave that. And then x minus x1, which is negative 1 plus root 5 over 3. And then you also have y minus 2 plus root 5 over 3 equals x minus negative 1 minus root 5 over 3. Okay. Right, that's number 9. Find an equation of a tangent line. Let's do number 10. All right, so number 10, we have this. Again, looking for tangent lines, all that same good stuff. So need y prime, need product rule. So negative 2x sine of x, and then plus negative x squared cosine of x. Then I'll evaluate this for x equals 3 pi over 2. Sorry about that. So negative 2 times 3 pi over 2 times sine of 3 pi over 2 minus 3 pi over 2 squared times cosine of 3 pi over 2. So writing all that out, actually, just to save us a little bit of time, if you use, make sure to use radians, by the way, in your calculator, and you're getting 3 pi. So that's the slope. So in other words, y minus, and that'll really turn into plus. So I'll just say y plus 9 pi squared over 4 equals 3 pi x minus 3 pi over 2. And I believe if you wanted, if you were asked to leave that in slope-intercept form or something, you would get y equals 3 pi x minus 27 pi squared over 4, I believe. But check me on all this. That's number 10. I'll do a couple of these from number 11. So these chain rule problems. I'll do this one. I'll do part 1 and part 3. So to find f prime of x, I'm thinking of the outermost function as this square root function. So in other words, I'm really thinking of this as like x squared plus 3x to the 1/2 power. So to take this derivative, I'm starting with this outermost function, which is the 1/2 power. Reducing that 1/2 by 1 takes us down to negative 1/2, but then I need to multiply by this chain rule d dx of x squared plus 3x. Simplifying all of that, right? Taking this derivative, bringing that over, I can rewrite this in the denominator, all that good stuff. I can say 2x plus 3, that's the chain rule derivative part. Sorry if that was hard to see. Derivative of this, right? 2x plus 3, then all divided by 2 times the square root of x squared plus 3x. Let me see if I missed anything. I don't think so. take a quick peek at the key to make sure things look similar, and things do look similar. Okay, so skipping this, check out the key online for the others. H prime of theta. So H prime of theta will be the derivative of the outermost function, which is sine. So derivative of sine is cosine, and then we'll have theta cubed plus theta. Then multiplied by dd theta of theta cubed plus theta. So derivative of theta cubed plus theta, it's not too bad. I'll bring that out front actually. I'll have 3 theta squared plus 1 times cosine of theta cubed plus theta. Okay. Check out the cue for the others. Let's go on. All right, number 12. I'll do part 2 actually. I'll do part 2 and then I'll leave the key for this one. So for part 2, the outermost function, this is like a series of chain rules. The outermost function is this sine. So that'll be the first function that I differentiate. So I'll get cosine of sine of x. Then times ddx of what was on the inside, cosine of sine of x. So now we're differentiating the cosine part. That's now the outermost piece of this function that has still yet to be differentiated. So derivative of cosine is negative sine. So we'll have cosine of sine of x times negative sine of x. Sorry about that. And then times, so I just differentiated cosine, so now I need to multiply by ddx of sine of x. Derivative of sine of x is cosine. I'll bring this negative all the way out front. So negative cosine of sine of x times the sine of x times cosine of x, which is the derivative of sine. Okay. All right, so find the equation of the tangent line to this curve at pi over 2, 0. So y prime is needed. The chain rule is needed for that, so I'll have cosine of x times derivative of cosine of x. All of this amounts to cosine of x times negative sine of x. Okay, so I have y prime as cosine of x times, and this, I'll actually bring that negative all the way out front again, and then times sine of x. So I now need to evaluate this derivative at pi over 2 to figure out what slope to use. Okay, the cosine of pi over 2 is 0. The cosine of 0 is 1. So I have negative 1 times 1. So this is negative 1. So in other words, our slope is negative 1 for this tangent line. So putting it together with the point, we have y minus 0 equals negative x minus pi over 2. It's probably better just to leave that in slope-intercept form. So y equals negative x plus pi over 2. Okay, so that's number 13. So 14, this implicit differentiation. So dy dx, if we're looking for that, that's the same exact thing as y prime, by the way. So what I'll do is I'll go term by term. Whenever I take a derivative of a y term, I need to appreciate the fact that y would itself be a function of x, so I'll use this chain rule notation. So derivative of x squared is just 2x. No need for a prime notation because that's an explicit function of x. Y squared is an implicit function of x, so I'll have plus 2y, but then times dy dx. I could also write just y prime there. Derivative of 9 with respect to x is 0. Now isolate dy dx. So subtract 2x. So 2y times dy dx equals negative 2x. Divide by 2y. So dy dx, in other words, equals negative x over y. Find the equation of the tangent line. So this is our kind of access into the slope. This is the point that we care about here. So if you evaluate dy dx at x equals 1 and y equals 2 root 2, you're going to find the slope of the equation of the tangent line to this curve at this point. So we'll have negative 1, right? I'm plugging now these points, these components here. So 1 goes in for x and 2 root 2 goes in for y. So that would be our slope. If you want to rationalize that, you can write this as negative root 2 over 4. So maybe I'll use that as my slope. So in other words, y minus 2 root 2 equals negative root 2 over 4 times x minus 1. This would be the point slope version of it. I believe if you simplify, rewrite it, you can say the slope-intercept form as y equals negative root 2 over 4x plus 9 root 2 over 4. That would be that slope-intercept version. Graph it. I'll really just kind of suggest looking at the key, but basically it's a circle centered at 0, 0, radius 3, with this tangent line going across it somewhere like this. But, all right, that's number 14. Let's look at 15. So again, finding this implicit derivative, right? We cannot get y alone here. So y is kind of stuck there. So to fully differentiate it, we're just saying, okay, anytime I come across a y, I'm going to appreciate the fact that y is a function of x, really. So a chain rule would need to be applied. So derivative of cosine is negative sine. And then I have x minus y. And then I need to multiply by d dx of x minus y. Hi. Can you go, Mama? Okay. Can you go back to Mama's room? Okay. All right, so sorry about that. So now moving to the right side, I am about to take a derivative of something involving y, so that'll be 2, but then I just need to multiply by dy dx, that chain rule. So I still need to do this part, this derivative. So negative sine of x minus y. Derivative of x is 1. Derivative of y is also 1. So I'll have minus dy dx. Right? Derivative of negative y would be negative 1, and then I'm multiplying negative 1 by dy dx. Equals 2 times dy dx. Now what I need to do is get dy dx is on the same side, everything else on the other side. So distributing. So negative sine x minus y plus sine of x minus y times dy dx equals 2 dy dx. Right, get these two on the same side and then divide by the rest. Kind of running out of room, but what you're going to get is dy dx equals sine of x minus y over sine of x minus y minus 2. So now find the equation of the tangent line. So what I'll need to do is now evaluate our derivative at this point here. So dy dx evaluated at x equals pi over 2 and y equals 0. So this gives us the sine of pi over 2 minus 0 over the sine of pi over 2 minus 0 minus 2. Simplifying that, sine of pi over 2 is 1. Then I get another 1 minus 2 on bottom. This is 1 over negative 1. That's negative 1. This is the slope of the tangent line. So y minus 0 equals negative x minus pi over 2. And that would, sorry about that. So this is what I was just saying. And now we have y equals negative x plus pi over 2. All right, I might need to go soon. Let's see. I'll do one more. So 17 here, this logarithmic differentiation. For the others, please navigate to the key, okay? But I'll talk about 17. We have x raised to the 2x squared. So the move here so that we could differentiate is to apply a logarithm. So I'll say log y equals natural log of x to the 2x squared. Because a logarithm is applied now, I can bring out this exponent as a factor. So I can say ln of y equals 2x squared ln of x. Now I can differentiate this implicitly. So anytime I approach something with y, I'll need the chain rule. So I'll have derivative of ln of y is 1 over y times chain rule y prime. On the right, I have two functions of x. I need the product rule for this. So 4x ln of x plus 2x squared times 1 over x. Simplify a bit. So I have 1 over y times y prime equals 4x ln of x plus 2x. Multiply both sides by y to get y prime, which is the derivative. So y prime equals y times 4x ln of x plus 2x. Now replace y with what y is. So in other words, y prime, the derivative of what we started with, is x to the 2x squared times, well, I guess I could even factor out. Maybe I'll just do that as well. But y prime would be, I could factor out actually a 2x out front there, and then that would leave behind 2 ln x plus 1. So that's one way of leaving the answer. I think what I did on the key is just say y prime. Let me make sure this matches up. So I did factor out. I kind of wrote it this way though. I said 2x on the left, and then 2 ln x plus 1, and then x to the 2x squared on the right. So same thing. Okay. All right. That is going to be all that I can fit into this video. Please reference the key. Talk to you guys soon.
So yeah, would you like, let's see how this one goes, because if I make one up, I want it to be kind of interesting. Yeah, would you like to do this exact one, Emma?
It could be that one or a similar one. I kind of just, that was like the one that didn't get into the video, so I just wanted to like make sure, like I saw your method.
Yeah, let's go exactly through this one.
Okay.
All right. Cool, so yeah, we have this position function. All right, so I'll write this down. So this is number 18 on the practice exam. So yeah, we have a bunch of parts. I'll go through each of them. So it's 1 through 9. The first part is find the velocity at time t. All right, so we're given the position of the particle at time t. Right. The first derivative of position is velocity. Right, so for part 1, f prime of t will be that velocity as a function of t. So I'll have the power rule. 3t squared minus 12t plus 9. And that's leaving it at time t. That's what they mean. That might be a confusing part, is just what do they mean at time t? They just mean leaving it as a function of t at any time. Part 2. So part 2 says, what is the velocity after 2 seconds and after 4 seconds? So v of 2 would be 3 times 2 squared minus 12 times 2 plus 9. All right, so I'll type this in. So let's see. -3 And we're in units of, I see seconds. I don't see a distance unit. I'm trying to find one. I don't see one that I actually stated. That would have been an error. So we'll just go with feet, but it should have been stated. So this would be -3. And that would be something like feet per second, or meters per second, or miles per second. And then V of 4. Nine. All right, that's part 2. Part 3. Kind of going quickly through these. I imagine it's the later parts that are more troublesome. But part 3. Let's see. When is the particle at rest? So yeah, there's a couple ways of figuring that out. But probably the main way would be using the velocity function. Right, the particle will be at rest when the velocity is 0. So we'll have 0 equals 3t squared minus 12t plus 9. Can get rid of a 3, divide away a 3. And factor, so it'll be t minus 3. And then t minus 1. So we have 1 and 3 as our times when this velocity is 0, right? Solving these, set equal to 0. So I'll have t minus 3 equals 0, or t minus 1 equals 0. That zero product property from algebra. Add, so that's where the 3 is. That's some sort of time unit. I'll say seconds. Well, I think it actually did say seconds. And then 1 second. Cool. Yeah, part 4. When is the particle moving in the positive direction? So yeah, velocity is not only how fast, but it's also a record of direction. So velocity is what's called a vector. It's a vector quantity. So you know both speed and direction. Speed is what's called a scalar. It's just an amount. You don't know in what direction that amount is going. So anyways, we'll still use the velocity function to answer a question about directionality. Okay, so for part 4, positive direction, we can say, all right, when is that velocity function positive? Right, just conceptually. So positive direction when v greater than 0. I'll say greater than strictly. All right. So yeah, we have a parabola. That might just And we also know that we have zeros here at 3 and 1 for this parabola. So it's a picture that looks something like this. If this is 1, this is 3, then we have a parabola doing something like this. Right? Why do I know that? Well, because we got those zeros. From this function, we set it equal to 0. We know that it's 0 right here at 1 and 3. I know that it's opening up because of this positive number here, right? That a value on the quadratic tells us that it's opening up. So I know that this is the picture, essentially, right? There's some positive region, and some negative region in between. So moving in the positive direction when the velocity is positive, right? The velocity is positive, it looks like between 0 and 1. So I'd have 0 to 1. And then it's also positive from 3 to infinity. I don't know if I had this extending to infinity. Yeah. Yeah, it doesn't say any restriction at this stage. So union 3 to infinity. Be part 4. Moving in the positive direction. Part 5, find the total distance traveled during the first 5 seconds. Okay. Yeah. All right. So yeah, you can kind of start to draw a picture of the position function. That would be a fine way of doing this. So I'm going to erase everything over here now. So I'll sketch the position function as a way of figuring out how far this thing has gone. So here's 0, obviously, 0. And then maybe I'll look at these interesting moments when the velocity was 0 as well. So maybe I'll kind of identify those, right? Since I know there were moments when the velocity was 0, that could be a moment when the thing turns around. You can have 0 velocity though, and then not turn around afterwards. But something else you can point out from this graph of the velocity curve is that the velocity went from positive to negative. So that does mean turning around. And then it went from negative to positive. So it looks like we have 2 turnarounds. From the position, let's start to identify these points. So we have 0, 0, right? Where is it at t equals 0? Well, everybody has a t. So that means at t equals 0, the position was 0. This particle was right at the origin at 0. It didn't have to be that way, right? If this term didn't have a t, then at 0, it would be at 9. It would just be sitting here at 9. Whatever. But this thing does have a t. Okay, what about at 1 second? Where is it, you know? And let's plot that. So I'm going to plug in 1. I'll find f of 1. Just getting some information about the position curve, that'll help a lot to figure out how far it went. So plugging in a 1, I have 1 minus 6 plus 9, which is 4. So this is 4. And then let me actually see what 3 is, just so I know how the scale needs to be. Okay, I got 0 actually. All right, so this thing goes up. Oh, let me write down what I got. So it was f of 3, I got 0. Let me know if you get something else. Okay, so this must go up from here, right, and land somewhere at 4. I'll call this 4. So it moved along this line, just to be clear. It's going this way. Well, yeah, I'll just leave it open, but it's going this way. And then slowing down, it's not getting smaller. Okay, so I'll just connect that. At 3, it's at 0. So it comes down here. And then just to get some more information, maybe I'll check out what it's doing at 4. But I should know actually what it's doing over there. It's a good way to know already. But just typing in the 4, we get a 4. So this thing comes back down. So if this is 4, just to like look at an extra location, then it's actually up at 4 again. So it's doing kind of that. Okay. So, and then it said all the way to what time? Let me see. It said during the first 5 seconds. So I need to actually figure out to the 5th second. So I'll go even one more second. I forgot about that 5. So here's 5, let's say. And let's figure out where it is then. This might be way off the page, I hope not. Oh gosh. Okay, I got 20. So I'm just going to call 20 right here, even though it doesn't look very great. Okay. But we'll just know that all the way up there, there's a 16, gap. Here's a 4 gap. Sorry about that. All right, so I can see it went up 4, then it went down 4. Right? Then it went up 20. Right? So that would be the distance. So it would be this 4 plus 4, right? It moved back down, but whatever, that's just distance being traveled. And then it went from 0 up to 20 in that last 2 seconds. Okay. 28. And I guess that would be feet, whatever that distance unit was there. All right, so that would be part 5. Oh, I see. All right. So part 6 says draw a diagram to illustrate the motion of the particle. I'm gonna not do that because I've essentially done that here. And there's not a drawing option on WebAssign anyways. So, but this would be a drawing anyways. This is it going up, down, and then up, right? But yeah, just to be clear, it is not moving. Well, it may be, I don't know. But we don't know that it's moving in this arc. That's not the claim, actually. The claim is that it's moving up here in this amount of time, then it's moving back down here in this amount of time, and then it's moving all the way from here up to here in this amount of time. Right? We only have one spatial dimension of information. It's just a position time function, right? And that position is only given with respect to the vertical axis. We have nothing else. Anyways, so yeah, part 6, I'm calling that kind of done as well. So this is like part 5/6 for me. Part 7, find the acceleration at time t and after 4 seconds. All right. So yeah, that velocity function was that first derivative. So the acceleration will be f double prime. Right, this was f single prime. So we'll have 6t minus 12 there. So that would be the at t part. And then at 4, we'd have a of 4. So 24 minus 12. So 12, and that would be feet per second squared. I should already have those units there though. So part 7. Good, good, good. All right. Part 8, graph the position, velocity, and acceleration functions for 0 to 5. And I would use Desmos for that. And then they might provide you with like a multiple choice. I think that's what they've been doing. So I'm going to go to Desmos and type these things in. All right. So yeah, we had our original one. I'm going to use x's. Right, something you can do is restrict it with these braces. So you can go 0 less than or equal to x less than or equal to 5, semicolon. Oh, sorry, colon. Semicolon, I forget, what is that, a semicolon or colon? Someone let me know. And then maybe I'll duplicate this. So I can go duplicate, duplicate, just to make it a little easier. And then I can take the derivative, right? So 3x squared minus 12x plus 9. Maybe I'll make that blue. And then take the derivative of the derivative. So I'll have 6x minus 12. Maybe make this one green. Yeah, I can change the axes, right? Maybe go from -1 to 6. And then looks like it's going off the screen, so I can change the y as well. I can say maybe -17 to 17. Will that do it? I guess it's close enough. Okay, so there's our curves we have the position in red, velocity in blue, and acceleration in green. So that would be my, what was that, part 8. So I'll write that. Part 8 is on Desmos. Okay. Part 9, when is it speeding up and slowing down? Okay. So speeding up. Let's talk about it. And really that Desmos graph is going to be super helpful for this last part. So for speeding up, we have A and V, same sign. All right, for slowing down, we have A and B, opposite sign. All right, so there's 2 ways to do each. You can have plus, plus, or minus, minus. For speeding up, for slowing down, you can have, minus plus, or plus minus. Okay, and by plus minus, we're talking about the outputs, like the literal outputs are positive and positive. Or the literal outputs are negative and negative. So this would be both of them below the x-axis or t-axis. This would be both of these functions above the t-axis. This would be opposite sides of the t-axis, right, for A and B. Right, one's below, one's above. This would be the other type of opposite where one's above and one's below. Okay, so we can look at Desmos and learn all of that now that we have these here. So let's talk speeding up first. So I'll just write it over here, I guess. So for speeding up, we're looking for plus plus, and we're just talking about A and V. So I'll turn this one off. Okay, so let's talk speeding up. I'm looking for plus plus or minus minus. So here's opposite. And then here's a moment where they now have the same sign. Here's minus minus, right? After this moment, 1 second, they now are both negative. They're both below the t-axis, right? So for speeding up, I'll have a moment where that begins at 1, and then it'll continue for a little bit, right? They're still negative, negative until this moment in time, until 2. Then the acceleration goes positive while the velocity is still negative. Okay, so we'd have at 2 seconds, that would end. But then over here at 3, they're now both positive, right? So from 3 to 5, they're actually both positive. So that's speeding up all throughout the end of that. So 3 to 5. Okay.
Professor, there's no restriction in here, so Could we just say that it's go to infinity instead of 5? Because in the question, there's no.
Oh, okay, let me see. Because yeah, it depends on what the statement is. Yeah, it doesn't say, you're right, it doesn't really say, you know, to end the discussion ever. Right. So I like your point. So yeah, I'll make that, instead of a 5, I'll make that an infinity. Good. For slowing down, let's go back to the graph and we'll do the same thing. It'll be elsewhere, right? Just basically elsewhere, it'll be slowing down. But let's just make sure. So slowing down, we're looking for opposites. So yeah, here was that opposite. And then they became the same right here at 1. So from 0 to 1, there's our first chunk of slowing down. And then they're the same for a little bit. But right now, at 2, they're opposite until 3. Right? Here's them being opposite. And then at 3, here's them being positive. Right? So from 2 to 3, we have union, 2 to 3. Good. All right.
Professor,
Yeah.
if we are asked to show our work with the depending on the decimal of the graphs, is there any other written way that we can do it? Can you show us a little bit?
Yeah, like how to do that more algebraically, you're saying?
Yes.
Yeah, so let's see. I would, I guess, make a sign chart for both. But the sign chart is just like the graph also. So, but I think sign chart would be my advice. Let me write down over here what I mean by that. That's fine. So I do a sign chart for like the velocity first, maybe. So what I mean by that is I'd set up a timeline for the velocity, and I put the zeros that we had for the velocity here. I think it was 1 and 3. So I know that it's exactly 0 here, right? So that means it'll only be either positive or negative here, or positive and negative here. It won't be 0 elsewhere. These were the only zeros. So I would do a test now. So I'd test, like make a test point at 2. Our velocity was what, 3 minus 12t plus 9, I think. Right, so if you check it at 2, what is the sign? That's all I care about. So we'll have what? 12 minus 24. We have negative, it looks like. Right? So 3 times 4, 12, minus 24, negative 12, plus 9, negative 3. So we have a bunch of negatives here. Let me write that down. So here I know the sign of the velocity between 1 and 3. Then I can test outside of there. Right? Maybe I'll test over here at 5. Maybe I'll test over here at 0. So at 0, I have a 9. So it's positive over here. Over here at 5, well, plug that in. You'll get 25 times 3. So you're already up to 75 minus 5 times 12, just 60. So you're at 15. +9, you're in positive land. And that's all we care about, is just plus or minus. Okay, so here's all the information regarding signage for the velocity of the particle. And then I might do the same exact thing for the acceleration. And kind of mapping it in the same way. For the acceleration, we had 6t minus 12. Right, so if I just kind of highlight, here's one. I'm not saying I'm using these as my markers, but just to match and compare, because we're going to be comparing in a second. Our 0 would happen at 2, right? Right here at 2, we get a 0. So here's my 0, actually. Right here at 2. These are just for comparisons from above. So on the left side of 2, I can test, right? I can test here at like 1. That's fine. I'll use 1 as a test. So that's negative, right? Plug in the 1, 6 minus 12, -6. So it's negative throughout here. I know that it's exactly 0 here. So it's 0 nowhere else. On the right-hand side, I can test at 3. There's nothing wrong with that. So plug in a 3, 18 minus 12. So it's positive now. Okay, so again, it's like a visual comparison with respect to signage. It's not very algebraic. But this sign chart is going to come up in a big way. So this is also a way of just kind of systemizing it and organizing the work, right? It's not very algebraic other than finding these zeros. So anyways, I would now compare, all right, where do they have opposite sign? Well, they have opposite sign from 0 to 1. Here's opposite. Right, so that would be slowing down here. And then from 1 to 2, they have the same sign actually. They're both negative. So that would be speeding up. And then from 2 to 3, I have opposite again. So that would be slowing down, right? Slowing down, 2 to 3. And then from 3 on, I would have same again. So that would be speeding up. All right. Okay. Good. I'm glad we got this recorded. What else?
So I got a question. It's from the quiz, so we don't have to go too deep into it, but it's about the expression in a denominator.
Sure. Yeah. Which number?
It was number 14 from the quiz.
Okay. So quiz 4, 14.
Yes, sir.
All right.